All right, last time we started section 4.3, and we'd gotten a little bit of ways into it. We're going to continue working in 4.3 today. And let's find out where we were. I'm showing right there. Does that look good to you guys? Prime factorization method. All right, so last time we had done one method. The method we had done was this intersections of sets method. Obviously, if our sets are really small, this is pretty convenient. We can just write them all out, and we can look for the biggest one. So let's take a look at what happens when they're not so small, because I don't know about you, but I don't really want to write out all the factorization for 400. It's going to go, not primes. That's what we're about to show. But if I actually listed all of the factors out for 400, that'd take a little longer than the last problem. So that's not always the best choice from the last example. So one way of doing this is to do the prime factorization method. So in this method, we actually find the prime factorization for each of the values we're looking for. We look at whatever prime factors they have that are in common. Okay, so that phrase common is important right here. And then we list each prime that they have in common with the smallest exponent. That step 2 and step 3 should feel like we've already done this. You guys had me do 2 of them on the board when you did questions, didn't you? Where we looked at different values and we factored things out they had in common. That's all this method is. And then the last thing then is to actually multiply them out or to find the product from that value set. Okay, so to keep us on our... I'm going to use that same notation that we used last time that you were probably less familiar with, and we're going to do our factor... I don't have a name for this. I should come up with a wonderful name. Maybe that should be a contest. I should see who can come up with the best name for my method of doing this. It should be the hands method. Oh, that's a good name for it. Maybe we should go with that. Let's try the hands method for writing these factors out instead of the prime, the factor tree. All right, smallest number that divides 400. We're looking for primes only here. 2. If I divide it by 2, what do I have? 200. Now what? Do again, and I get 100. Then what? 2 again, and I get 50. And then? We're going to do 2 again. We will do 5 next, though, Hannah. I think you were a step ahead of me. Yeah, so this one gives me 25, right? Yeah. And then Hannah wants me to divide by 5. And I'm done, right? Okay, let's actually write this one out. So this number was originally 400. In prime factorization, this is 2 to the what? How many 2's do I have? 4 of them? Times 5 to the what? Squared. Okay, we're going to do the same thing now with 360. Smallest number that divides 360. 2. What do I get? 180. Divisible by 2. What do I get? 90 divisible by 2. What do I get? 45. Resist the temptation to skip one. What's the next factor? It is 3. You guys wanted to do 5, didn't you? All right, so let's say 45 divisible by 3 gives me 15. 15. 15 divisible by 3 one more time. 3 gives me 5. So the number, we'll put these together. Oops. So there was 400. Let's do 360. So 360 is 2 to the third times 3 to the second times 5 to the, well, first, if we want to write 1 or write nothing there, correct. We could write nothing beside it. So what do they have in common? So this is the GCD. What factors, prime factors, do they have in common? What do you, 2's and 5's. How many 2's is the smallest number of 2's they have in common? They actually both have 3 2's, at least 3 2's. And how about 5's? 1. So multiplying these out now, what's 2 cubed? 8. And 8 times 5 is 40. The greatest common divisor is 40. Any questions on this one? Okay, so you're looking for the prime factors they have in common with the smallest exponent. Okay. I like this one a lot. This is called the division by primes method. My numbers are different now. I have 410 and 360. So what we're going to do is we're going to write the numbers in a row. We're going to look for something that divides both of them, that is something that they're both commonly divisible by. It doesn't have to be a prime, but for the method it's going to use a common prime. But if you did it without primes, it would actually still work. We're going to divide the quotients by that prime factor, and then we keep repeating until they can both not be divisible by the same thing any longer. Okay? And then the greatest common divisor is the product of all the primes. So let me show you how this works. We write the 410 and the 360 sort of beside one another. And we're going to do the division kind of like I did the division on the last problem, but we're doing it at the same time. So what is the smallest prime number? And it doesn't even have to be smallest, but just because it's the same sort of a setup, I'm going to say smallest. What's the smallest prime number that divides both of these? 2. So what is 410 divided by 2? 205. And what is 360 divided by 2? 180. All right, that looks good. We look for another prime that divides them both. Okay, so 2's out, right? That doesn't work. How about 3? Not going to work. 5? Yeah, 5 will work. So what is 205 divided by 5? 41. How about 180 divided by 5? 36? All right. Now we take a look at the 41 and the 36, and what do you see? They have nothing in common. 41 is actually a prime number, so that's not good. If you weren't sure if 36, I'm sorry. If you weren't sure that 41 was a prime number, you could look at the 36, and you could say, what else divides the 36? Well, you could say, oh, well, 2, but 2 doesn't work over here. And you could say, oh, well, 3 works, but 3 doesn't work over here. You could sort of just go through the things that you know divide 36, and very quickly you'll find out none of them divide 41. So even if 41 weren't prime here, if you get to this point and you recognize they don't divide by anything else in common any longer, you're done. So your answer then is right here. Your GCD is 2 times 5, which is the wonderful number 10. It's kind of a handy-dandy one. We don't look for anything in common when we're done because we already did the common part of it when we were in the midst of doing it.
So you stop when you reach one prime number?
You stop when you reach numbers that don't divide by the same thing any longer. So if this number had not been 41, but it had been, say, 45, that won't work. How about 42? That won't work. Trying to find a number that it would stop with. Yuck. 45 won't work because it's divisible by 3, so it's 36. But these do not, neither of these actually have to be prime for you to stop the process. They just have to have nothing in common. Okay. So you could have numbers, like you could have a number 15 and a number 32. I think that would work. If I had 15 and 32, neither of those are prime. They both divide by things, but they don't divide by the same things any longer. That's what you're looking for. All right, the last one that is in this section is the Euclidean algorithm. I think I have time to do it with you. We'll see. The Euclidean algorithm is probably the most different than the rest of them. It's the most unique. So what you do in the Euclidean algorithm is you divide the larger number by the smaller one, and then you work to divide the previous divisor by the remainder. You repeat step number 2 until you get a remainder of 0, and the last divisor is the greatest common divisor. It sounds like there's a lot of terminology there. The process itself is not very difficult. So let's do the first step because you understood what that meant. Divide the larger number by the smaller one. Everybody understood that just fine, right? No problems there. Larger number, 126. Smaller number, 72. Got that. How many times will 72 go into 36? Once. Once. It goes in one time, and we subtract the 72. What's my remainder? Oh, 72 goes into 126. Oh, I said it wrong. I'm sorry. I'm sorry. I was probably still stuck back on 36 in the last problem. What's my remainder when I subtract here? 54. All right, so here's what I do once I get to the remainder. I use the remainder and the divisor, and I do it again. Okay? The remainder is now the number on the outside. What's being divided was the original number that I used on the outside, which is now 72, or was 72. Okay, so now I'm using the remainder and the number from the outside. How many times will 54 go into 72? Once. All right, and then we subtract. What's 72 minus 54? What was it? 18. Okay, so I take the remainder and the divisor. The remainder goes on the outside. The divisor goes underneath, 54. How many times will the 18 go into the 54? 3. And it does go in evenly, you're right. I get no remainder. At the point when you get a no remainder, a 0, the last number that you divided by is your greatest common divisor. And you could at least clarify for yourself pretty quickly that it is a divisor by simply using that number with the first two original numbers and seeing that it divides it. It is the greatest common divisor. Okay? This looks a little bit more mysterious, though. Wouldn't you agree? A little more hidden, a little bit more cryptic as to what's really going on behind the scenes. Yes, Gary?
So all these are just like different methods.
They are different methods for the same answer. You got it.